Welcome to the 7th distinguished lecture being organized by INA Bhubaneswar chapter jointly with SOA University and IMMT Bhubaneswar. And this is the 7th lecture in series. Every month actually we are trying to have 2 lectures, and also this thing actually will continue, and we hope and desire that INA National Convention in December will be organized in Bhubaneswar. In principle, they have agreed. I believe we require all your support to make it a grand success. Now, today we'll have a lecture by none other than Professor Subhasis De of IIT Kharagpur, and it is in a very important topic. And Professor De has been my colleague, so it is my real pleasure to welcome him on our behalf. So now, with this thing, I request our Professor P.K. Misra, distinguished fellow, and he has been also our colleague in IIT Kharagpur. Professor De must be knowing. So, to introduce Professor De. After that, our Honorable Vice Chancellor will speak, and if Professor Basu joins, then he will also speak a few words. After that, Professor De will give his lecture. Thank you.
Should I start? Or?
Yes, Professor Misra, please.
Yes. It's my privilege to talk something on Professor Subhasis De. Because that time, when I was at IIT Kharagpur, I didn't have much of interactions with him. I wish I should have. But because my topic is something different, and which I've been infused by my father, who is a man from hydraulics. And since my childhood, every child has got a love and affection for water. That's the most crucial thing. You can see how the children, they play with water, because nearly more than 75% of our whole universe, the world, is water. And our body itself says that it's water. And I could feebly remember my childhood days when I was about 3 years old. My father was working in Hirakud Dam project. He used to take me. Hardly I have not started schooling, but I used to always accompany my father. On the way, he will ask me to get down and play with in the old dumpers and tractors and all these things, like in the riverbed. And I used to play. And I don't know, I probably at that age 3 years old. And I used to see and watch. Then I have got an affinity for mechanical engineering. Then used to, in some other time, at a time, I used to run down from my house, our house, to the down the stream of Manadi, and see how the water is flowing. I was watching that one. And then I used to come back, ask my sisters, make me one paper boat. I used to go and run along with the stream and put that on the water and see how it is moving. Then I can see gradually the water becomes clear, and as it flows, and when it gets to a turbulent zone, that time I didn't know the turbulent zone, the boat will go inside and wheel around. I used to enjoy when the child plays. They watch what is happening. So gradually what happens, then I could see the miracle of what you call the hydrodynamics. That time I was not knowing hydrodynamics. That time hydrodynamics was not, hydraulic engineering was there. During the construction of what you call Munduri Dam project, and he was the design engineer and all these things, and he told that this, what you call, Mundur Dam should be constructed along a inclined direction. Then these administrators, they told, okay, we'll give it to Italy. Italian design came because the bridge construction has to, dam construction has to be perpendicular to the river. And finally what happened, after the construction, not after the middle of the construction, it completely collapsed. Then Gammon India was told, let's go to engineer Misra, Bijaram Misra, I should say, and he told,
সাড়ে পাঁচটা নাগাদ কে কে জয়েন করেছে, কজন জয়েন করে নামগুলো পাওয়া যাবে তখন? তুমি কপি করতে পারবে?
and then I saw
একবার
that,
দুবার
you see, that is that two rivers come at Naras, two rivers come. The interference is a turbulence, and the road has. But then finally, he convinced that it started with Biju Patnaik, and then the dam was constructed. You just mark Mundur Dam is inclined construction because the pillars supporting the what you call dam is not in perpendicular to the wall, but it's inclined in the flow directions. Then you see, I was taking training there. Gammon India was the construction. Then I could see how the old rivers turned into what you call old dormant rivers, into the what you call canal, flood. Canal, that's Puriman Canal, is, you see, distributing the water to all the places. Now, when you subsequently, I was always wondered how the flow pattern, because that time my father didn't know about what you call dynamics of the systems. But as I grow, I found the dynamics of water is very essential. Now, I wish I could have been with Professor Day, solving some of my problems which I tried to do at IIT Kharagpur. So I couldn't do that much. I was moving with structural engineers, what you call Professor Majumdar and all these things. And the Amacharya used to sit with me, and which was not seen in good direction, guided by our then director, Chopraji. Okay, he warned me that you don't go and sit there. I told nothing. I can't leave my friends. Okay. Anyway, so this is something you see, I don't want to tell myself, but these are my feelings. When I see a person who is working in dynamics, because I was trying to work on fluids used in cutting of human body. Now you might have seen dentists, they use water, saline water, to cut the tooth, decayed tooth. And nowadays the surgery is going to be in that action. The human surgery is most of the time eye surgery, done by water jet. And now for harder tissues like bones and all these things, it has to be pulsating. So that the dynamics part plays the dominant role because it produces stress more than the double. That Professor they must have experienced. That's why such a illuminating what biodata. I wish I could have been his student at this age. Anyway, coming to Professor Day, he's a professor of civil engineering, head of the department, professor department of civil engineering, and works on fluid dynamics. And his subject is everything. You see, hydrodynamics, turbulent, and sedimentation thing. It has got a lot of application in bioengineering application because today is health day. I couldn't resist myself to say that these are in surgery and everything where used will be much more better. And his so many things I can't express anything more than his biodata. I'm really stunned. He's a fellow from what do you call Royal Society, and that's great enough. Anyway, when I have to introduce Professor Day, I must say you are much more younger to me. You are my godfather, I can say. You have done. Please go ahead. Anyway, Professor Acharya can tell something more on Professor Day, but I don't know what to say. I'm seeing a God before me. Thank you, Professor. Please go ahead. Okay, please go ahead. Okay.
I request our Vice Chancellor, sir, please.
Good afternoon, Jai Jagannath. I must pay homage to Goddess Durga in Navratra. Today is 6th day of Navratra. Professor Misra are all esteemed Professor Dr. Acharya, the advisor to the university, Dr. Basu, our guest speaker, Dr. Subhasis De, and all the guests, those who are online. I think it's interesting that to know fluid dynamics. Dr. Misra become almost emotional when you're talking about biodata of Dr. Subhasis De. Of course, he is very brilliant and young and energetic. And regarding the university, this university is only started 2007. And repeatedly I have told that university's vision was to quality education, improving the healthcare delivery in and around Odisha, socio-economic development of the Odisha state, and above all, getting engaged in research and socio-economic development of people. To some extent, if you look at 25 years back, Bhubaneswar is a small town. I remember Bhubaneswar in late 50s, and when was not even an NSC. So from there, the Bhubaneswar is an educational hub. Today there are 15 universities in Bhubaneswar, and there are 5 medical colleges. If you look at only 20 years back, Bhubaneswar did not have a hospital worth talking about. Today we get patients from not only from all over Odisha, from neighboring states, maybe Chaubish Pargana, Mednapur, Jharkhand, and also neighboring Chhattisgarh. So we have to some extent fulfill the vision with which our founder president started the SWOT Trust in 1995. We have completed more than 25 years. As the trust, as a university, we are only 15 years old. So with that, we have done well. Coming to the ranking, we just got a QS ranking. Amongst the 35 universities in India, we are the one of them. I thank all our president, our founder president, all our deans and dedicated teachers and overall the researchers, postdocs and PhD students for their dedicated service, because it is not a single man's job. I thank all the vice chancellor before me, because 8 of them have already contributed their service in last 15 years or so. Coming to fluid dynamics, Dr. Misra was talking, there is nothing which is more better engineered than human body. Whether it is filtered through the kidney filters 180 liters a day and we only pass 1 liter of urine. How many hundreds of thousands of oxygen being passed through the capillaries of the lungs, and the blood pressure is nothing but the fluid dynamics. The water circulating the brain, cerebrospinal fluid has a dynamics. Because when we joined neurosurgery in 79, I was first thing the seminar was CSF dynamic. How the CSF is formed, how it circulates, how the pressure is being regulated, how get observed, and what are the shortcomings if something goes wrong in production, in circulation, and in absorption. So if you talk about the brain as a computer, the distance the stimulus travel from the foot to the brain is 25 milliseconds. And the response which goes from hand to the brain is 9 milliseconds. The blood which circulates from neck to the brain, the total cerebral circulation time is 7 seconds. When we do manual angiogram, putting a needle to the carotid artery, we used to do this in late 70s when I was a resident in neurosurgery. There is no sophisticated computer systems, there is no tomogram, there is no DSA or digital subtraction angiography which came in 80s. So what we used to do, anybody comes with suspected brain hemorrhage, we put a stick and needle, a real needle in the neck of the person and inject the dye, and somebody will be holding the cassettes, which is X-ray films, and he will be pulling out every second 1 or 2. So in 7 seconds, 2 for the arterial phase, 3 for the capillary phase, and 2 for the venous phase. So the blood circulates through the entire brain capillaries, 2 seconds for artery, 2 seconds for the capillaries, and 2 seconds. So can you believe what faster dynamics can be there when blood circulates the entire brain in 2 seconds? And I told kidney is there is nothing better filtered than the kidney. If kidney fails, what will happen we know. If the lungs fail, we know what happens during the pandemic. So entire human body, either fluid dynamics or mechanical engineering, computer engineering, storage capacity, and also high flow electrical stimulations. Your epilepsy is nothing but the electrical discharge will start from the brain and go whole over the body within milliseconds. So if I have to talk about more of the engineering, there is nothing which is more complicated than biomedical engineering. So when Dr. Basu Guha, Dr. Guha was the professor of biomedical engineering at AIIMS, he got very upset and he started doing MBBS in 1970. So he is the only engineer I know about that who, after being professor at Delhi IIT in biomedical engineering, which had a combined department of biomedical engineering at AIIMS Delhi and IIT Delhi. And he thought he's the odd man out at AIIMS, being a professor of biomedical engineering, and he went for MBBS from 70 to 75. And that's the year when I joined MBBS at Orampur. So it's just coincident that Dr. Guha and me joined MBBS almost same time, because he is the first batch MBBS from University Medical College, Delhi. I am not going to bore you, because if I keep on talking the engineer, God's engineering, you will not be able to accept it. It will all put down your egos, because whatever you little you have human being done cannot beat God. Because if we talk about mechanism of spine, hundreds of PhD have been done on mechanics of spine. Last one of my student who did PhD between AIMS and IIT Delhi, the movement at the brain and spinal cord junction, which is called craniovertebral junction, is so complicated and complex. And his PhD was, he took the cadavers, put the weight, and took them to the computer science like CT scan and MRI, and find out how much pressure put how much force at the craniovertebral junction. And he did over 10 cadaver and got a PhD degree from IIT on mechanical engineering, the mechanics at craniovertebral junction. Human body is very complex, so I'm not going to bore you. I think we have heard Dr. Misra. We are all eager to hear Professor Subhasis there. Of course, he is brilliant, and it is always goes without saying the younger generation are always more brilliant than the older generation. Older generation think the younger generation are gone case, and if the older generation think they are gone case, and younger generation think the older ones are more less brainy. So younger one thinks older are less brainy, and the older one thinks younger one are gone cases. Thank you very much.
Admitted, sir. Assignment. So, sir, out of how many we have to attempt, and now
Out of 30 marks, you need to have minimum 12 marks.
how many exams?
2 exams you can get 12 marks.
Okay. And we have to write final one exam. Is it online or offline?
Anybody talking about exam? What exam?
In which month it will there?
Anyway, Professor Basu is here.
Okay, so 26th April. Okay, this month.
Professor Basu, are you here? No.
Exam, sir.
So Professor De, kindly.
Yes, sir.
Respectable professor, am I audible? Respectable professor,
Yes, perfectly.
Chairman, INE Bhubaneswar chapter, Professor P.K. Misra, former mechanical engineering professor of IIT Kharagpur, Professor A.K. Mahapatra, Vice Chancellor of SOA University, Professor S. Basu, Director IMMT Bhubaneswar, Professor Renu Sharma, HOD Electrical Engineering, SOA University, Professor Nanda, Vice Chancellor SOA, Pro Vice Chancellor SOA University, Professor Rangaraju, former Professor IIT Roorkee and my idol, faculty members, researchers, students, engineers, learned audience. It's my honor to deliver a lecture and on a topic of sediment transport. I know from the audience there are many who can speak on the same subject, but I am here today because I am invited. Thanks for inviting me. There is a very small correction that I was introduced really in an elegant way, but still I am a learner, I believe. And the correction is that I am not the fellow of Royal Society of London. I am their editors, one of the editors of Proceedings A of Royal Society of London. That is their journal. And but I am the fellow of Indian Academy, Indian academies, that means sciences and also the engineering. So with this, I will share my PPT. Okay. Full screen. May I go for entire full screen mode or
Yes, sir,
maybe
you can go for entire full screen, sir.
entire full screen mode? That would be better. Yes, I will go for it. Is it visible now?
No, not yet.
No, not yet.
Please share.
I have shared my entire screen again. Pardon my ignorance. How can I share?
Professor Sharma, you please help him.
So you can just refresh the page, or you can log out and log in once again and
Yes,
reshare.
that will be better.
I have to refresh my page or I have to log in again. यशो तो तातरी
ये सर्वर ये कनेक्टिंग ही नहीं हो रहा। आप लोग लॉग्ड इन है?
हम इधर से एकदम बाहर चला जाएगा, एकदम लॉग आउट करके चला जाएगा साउथ।
हाँ सर, और एक बार रिस्टार्ट कर दीजिए कंप्यूटर वो लोग क्या कर रहे हैं वहाँ पर?
Sir, you have logged in once and try to share it now, sir.
Otherwise, actually, you get this thing presentation on mail and control from your side.
Yes, sir. If he can, sir can send it, I can share it from him. Sir, you asked sir to share with you so that it can be shared from our end.
Hello, I am Professor Kirti Sahu from IIT Hyderabad. Actually,
Yes.
Professor Dey is not able to log in now. Please call them.
All are allowed, sir.
अच्छा तुम सेटा पठेई दियो तो
Yes, yes.
please again send the link. Possibly got disconnected.
Allow को
ये बंद हुआ कैमरा आपका, ये भी ऑन हुआ. ओपन शेयर ट्रे, ये
this one.
ये वाला, this one. So professors, are you able to see Professor Dey's screen?
Are you able to see now?
Professor Sahu, are you able to see?
No, I am not able to see everything.
Oh.
Now, Professor Dey is login.
No, he's presenting now.
We are not able to see the screen.
मैं बता रहा हूँ इसको ऐसे नहीं करिए. Normally अभी रुक जाइए फिर से.
ये है.
नहीं सर, ऐसे ना कीजिए. बता रहा हूँ, पूरा विंडो शेयर कीजिए. प्रोफेसर साहू,
Yes.
is something visible now?
Nothing actually, no? So only I can see that Professor Dey is login.
सर इसमें कुछ है गिव कंट्रोल में?
तो उनको पूछिए थोड़ा इंफॉर्मेशन देने के लिए.
नहीं, हम लोग की आवाज आ रही है क्या उसमें कि नहीं आ रही है?
आ रहा है. मैं बोल दूं क्या? नहीं
हाँ बोलिए सर. आप
नहीं करूँ परमिशन दिया ही नहीं था.
ये स्क्रीन विजिबल होनी चाहिए.
Hello, madam. I am calling from. I am Kirti Sahu here. So
Yes, sir.
Professor Dey is saying that he has difficulties in sharing.
That's what, sir. If he can mail us, Damodar sir.
Are you able to hear him? Are you able to hear them?
We are able to hear them, sir.
Okay.
Rana, please request him to send this thing to me.
To whom?
I have to send my lecture to them. Shall I send my lecture to you?
Yes, that's
You
what they are saying.
please send these slides and we'll share from this side if there is any difficulty. Okay. तुम सेठी मोटा को ये करि परिबो तो हां तो मो मेल टा देखि कि तुम पठै दियो या को मैडम को हला. So, madam, you got it? Mail?
Yes, sir, I got it, sir. I'm opening, sir.
Now, please share from your side.
Is it visible, sir?
Yes, it is visible.
Thank you, sir.
Make it actually full screen. It will.
Yes, sir, I'm doing. Yes, sir. Is it visible now?
No, no.
Full screen, sir?
Not visible. No. Earlier it was visible. Now it is not there. Please.
Is it visible now, sir? Is
My
it visible?
my PPT is not visible.
देखा जाऊँ?
I can see. I can see.
I can see.
Yes, now it is visible.
कहाँ visible है?
Professor, they kindly start for it.
Vacant है? हाँ, तब
Ah.
बोले?
Now actually, you can, when you say next, then she will change the slide. Okay.
नहीं तो देखिए इसमें। It is not visible to me, Professor.
Oh, it is not visible to you.
Yes.
By God.
I think there is something wrong in his side. We can all see. We can all see.
Now we are able to see it. So what you can, do you have any other way where you can see the slide at the same time talk?
Yes, at the same time I can see from here.
Then you please go on talking and then actually you just say.
Okay.
You can tell me the slide number, sir.
First slide.
Okay.
I start my lecture. Okay, this is the first
Okay,
slide.
sure.
Yes.
Sorry for the trouble. Please go ahead.
No problem. Okay. Hydrodynamics of sediment transport from grain scale to continuum scale. The next slide, introduction. Is it okay for you?
Yes, sir.
Yes. The morphodynamical footprint of the rivers are created by the transport of the sediment by the river water. Here, the left-hand side picture shows the mature river. In the right-hand side, the braided river is shown. Now the same hydrodynamic footprints can be created in the laboratory as well. So there is a photograph of laboratory experimentation on the sediment transport. So this can be created in laboratory scale as well. Next slide. Sediment entrainment is driven by the water and the turbulence. Is it okay, ma'am? This is the next third slide.
You only have the first slide.
Dr. Professor Renu Sharma, is the main slide moving? I cannot see it moving.
No, it is not moving.
Dr. Sharma is not moving. It is same. The
Sir, I am
first slide.
here.
It will change.
Yes, now it
Yes.
is.
Now it is all right.
Yes.
It's okay now.
Yes. It's okay.
So now it is the third slide.
Yes, sir.
For me. Yes, sediment entrainment is driven by the water and the turbulence. The schematic diagram is shown for the sediment transport by the water flow in several modes, and also the turbulence, which cannot be visualized by the naked eye. it can only be visualized by PIV technique or by some other high-end technologies. Now, the hydrodynamic forces are acting on the sediment particles to transport them. This subject has attracted lots of famous scientists. Slide number 4. Even Albert Einstein, he was fascinated by the subject of fluvial hydrodynamics and encouraged his son Hans Einstein to pursue PhD on sediment transport. When he was asked about the profession of his son Hans Einstein, Albert Einstein replied that Hans is working on a more difficult problem than theory of relativity. It could be the perspective of Albert Einstein, but it carries lots of meaning. Therefore, he wrote a letter to recommend his son Hans Einstein. This is the image of Hans Einstein to pursue PhD on fluvial hydrodynamics. This is the handwritten recommendation letter by Albert Einstein. On another occasion, the Nobel laureate Werner Heisenberg, on his deathbed, was reported to have uttered, "When I meet God, I am going to ask him two questions: why relativity and why turbulence?" I really believe he will have an answer for the first. What about the second one? That's the turbulence. So it is such a complicated thing that even God would have no answer. That was the belief of Werner Heisenberg. Now coming to the science of the problem. In the top figure, you can see the sediment particles are exposed to the flow and it receives the stream flow. In fact, the hydrodynamic forces are induced due to the stream flow, and these forces destabilize the surface particle. The main forces are acting as a destabilizing force are drag force and the lead force, while the self weight or the submerged weight of the grain provides the stability. Now, with an increasing stream velocity, a state at the surface of the bed is reached when a few grains have started entraining to the main fluid body, and that is called the entrainment threshold of sediment. The entrainment threshold of sediment could occur in three different ways. Rolling mode. This is the slide number 9.
Yes, sir.
Yes.
Yes, sir.
So you are on slide number 9.
Yes, sir.
So it is the rolling mode, then sliding mode, and the lifting mode. In fact, as the base shear stress exceeds its critical value, that is the threshold value, grains begin to entrain in rolling mode and sliding mode. The rolling mode is possible if the particles are round enough. If the particles are not round enough, then the sliding mode is possible. Also, in case of the sediment transport for the round-shaped particle, both rolling and sliding are possible. In addition to this, if we increase the velocity of the flow further, that means if we increase the bed shear stress, then the grains are briefly lifted off the beds and perform series of short jumps called saltating motion. And here the lifting mode is active. So I have spoken on page 4. Next slide is page page 10.
11.
Next,
11.
next is page 11. Yes. So here I have shown a broken line which is considered to be the bed load layer. Within this layer, the sediment particle exchanges are going on in the form of bed load, and they are transported by rolling mode, sliding mode, and also the lifting mode in the form of saltation. Next slide, slide number 12. Today, sediment transport is very popular, and sediment entrainment occupies the central portion of the subject sediment transport. It is popular because of Shields, who has submitted a thesis, and his work has become a legendary work due to his diagram. And his diagram is popularly known as Shields diagram. This is the, I belong to slide number 13. This is the Shields diagram where the threshold Shields parameter is plotted against the shear Reynolds number. You can see the curve, and that curve represents the threshold of the sediment motion. Above the curve, the particles can move, and below the curve, there is no motion of the particles. Now the approach, what could be the possible approach to determine the sediment entrainment? The approach is a deterministic approach and the probabilistic approach. So here I have given a flow chart. In the flow chart, you can find for both the approaches, we first need to configure the bed. I belong to now page number 14.
Yes, sir.
So the bed configuration is to be known. Thereafter, the forces, how the forces are acting on the solitary particle, what could be the possible modes of sediment transport, then the force and momentum balances are required for the analysis, and we also need to know the velocity laws. Thereafter, after the discovery of turbulence bursting, we have understood the role of the turbulence towards the sediment. So that is why it is necessary to be included in the modeling. And finally, we come up with the results of the threshold. So this is the approach for both the cases. But in case of probability approach, we need to know the appropriate probability distribution function, which is applicable for the case of the instantaneous velocity fluctuations near the particle. And finally, we can come up with the probabilities of sediment entrainment expressions. So the criteria to improve the model, there are several existing models. I belong to slide number 15.
May I request all to keep their thing in mute? Some disturbance is coming.
Yes. So criteria to improve the model. We have to consider three-dimensional configuration of the model properly in addition to this, we have to go for the appropriate velocity and turbulence intensity laws, in addition to the rigorous analysis of the force system. Next slide, slide number 16. Thank you very much. This is the bed configuration. You can see the bed particles are shown by the yellow color, and the solitary particles are there in red color, dark red color. Now, due to the flow, first of all, the solitary particles are entrained. So they are present in the scattered form. Now, if we consider the three-dimensional force system, go to the slide number 17, then we can see the hydrodynamic forces are acting. The velocity profile is shown because of the fact we have the rough bed. So the appropriate velocity profile is to be taken here, which is nothing but the universal logarithmic law. At the near bed, in fact, it is valid. On the solitary particle, here its color is green. The drag force is acting, then the lift and the submerged weight. Two kinds of particles are chosen here. The bed particles have a size which is different from the solitary particles. In fact, the natural river bed has a sediment layering in a very regular pattern because of the fact it is not mixed up by the human. It is deposited naturally or even sorted out or washed out by the natural process. So it is in fact the water worked. So if it is water worked, the layering are also in a given form, that either if it is the particles are deposited, either the larger particles are underneath the bed, and at the top layer we have the finer particle. And when we consider the washing out, then the larger size of the particles are exposed, leaving the finer particles underneath them. So, and there are several other mechanisms like armoring and other things. I am not going into the details of those things. Now I'll go for the force analysis. Slide number 18. Here the force system is shown in three-dimensional form. The drag force and the lead force. Drag force is not acting at the center of the solitary particle because of the fact the velocity distribution is not the free stream velocity distribution. It is zero at the zero velocity level and gradually increasing with the vertical distance. So the drag force is shifted off the center. So here we have to be careful to take into account the moment of the drag force and also the position of the drag force. That can be achieved if we study the geometry of the force system very precisely. Now, if we join the centers of the solitary particle with the centers of the bed particle on which it is resting, the possible configuration is that a solitary particle can rest over three bed particles. I belong to slide number 19. Now, I belong to slide number 19. Now here Uh, the the left diagram shows the tetrahedron formed by joining the centers of the solitary particle and the bait particle, and just below that figure, the solitary particle is considered to be transparent here in order to visualize the bait particles. We can see C1, C2, C3 are the centers of the bait particles, and C is the center of the solitary particles. So this is the geometry. And these solitary particles can roll uh, in any direction depending on and according to the orientation of the bed particle and also the flow direction. Because in the river bed, there could be numerous orientations of the particle and also the flow direction could vary. Now the point we have to keep in our mind that what are the two extremities by which the solitary particle can roll. Here I have shown by the two arrows. The solitary particle can roll, this is one of the extremes, over the valley formed by the two bed particles, C1 and C2. This is the easier way to travel. Otherwise, the solitary particle can also roll over the summit of a single particle, that is C2. So these are the two possible routes for the solitary particle to roll over, to dislodge from its own position. Now, from the geometry, because ultimately we have to take the moment about the pivoting point, and that also we have to determine precisely. We should know the several linear distances. So this is delta. Delta is nothing but the distance between the vertical distance between the bottommost point of the solitary particle and the virtual bed level. Coming to the virtual bed level, it is not that easy to fix the virtual bed level through which we consider our x-axis. How can we fix this? There are several ways, several empirical recommendations to determine the virtual bed level, that is the axis of the system coordinate system, x-axis of the coordinate system. One of the recommendations is that we can consider the virtual bed level so a fraction below a fraction of the bed particle, that is given here, chi into beta. Chi is less than unity. But in fact, the virtual bed level is to be finalized from the velocity profile. If we have the data, we consider here the zero displacement level. So by fitting the logarithmic law, considering the zero displacement level, there is a methodology given by Vladimir Nikola and also Katinka Call that can also be followed. So anyway, this is the problem of sediment transport, and here we can assume the virtual bed level is passing through 1/4 of the diameter of the bed particle. About the possible rolling of the particle, of late I told you that there could be two limits. The grain can roll over the crest of a bed grain or can roll over the bank formed by the two neighboring bed particles. Now from the geometry, in the right hand side, we can show the two roots, one JP and another one JC2. JC2, when the particle rolls over the crest of a single grain, this is one case, and if the solitary particle rolls over the flank formed by the two bed particles, then it would follow JP root. So this is obtained from the tetrahedron developed by joining the centers of the particles. Page number 22.
Yes.
If the grain rolls over a single particle, then the pivoting angle, that is phi at the top, becomes maximum. Otherwise, if the particle rolls over the flank formed by the two particles, then the pivoting angle becomes minimum. But it moves over. Anyway, from the geometry, we can calculate the minimum pivoting angle and the maximum pivoting angle. Now, page number 23, first. Yes, here we can determine the pivoting angle from the geometry, and then page number 24. Then page number 24, where we can show the particle follow the two roots, and finally the distributions can be numerous. So therefore it is prudent to consider the uniform distribution, and therefore we should consider the particle roll, the particle follow the midway of these two extremes, because finally it is required to determine the lever arms, and accordingly the pivoting angles are calculated. Page number 25. Yes, this is the mean pivoting angle. So if this is done, then we can go for the force analysis. Page number 26. Thank you. So the forces are drag force, lead force, and submerged weight. Next page. Yes. The submerged weight can be calculated considering a spherical particle. In this way, if the particle is not spherical enough, then we can use a factor. Next page. Thank you. The instantaneous drag acting on the particle can be considered in this way. Here, the drag is considered to be a function of dynamic pressure. The area exposed to the flow is not the full area of the particle. Because of the fact, we have to remember the particle is resting, the solitary particle is resting over the bed particles. And also we have to remember the zero velocity level. So below the zero velocity level, it is not that significant. So depending on the position of the particle, and which can be determined from the ratio of the diameters of the bed particle to the solitary particle, but the position of the particle, and then accordingly the area can be calculated. I will show you how to calculate the area. Next, we have to take the moment of the force system. So this is the way, and also the drag is not acting through the center. So this is the only way we can determine the height of action of the drag force, which is definitely not at the center but elsewhere. Thank you. Next. Next.
Elevations.
Yes. So this is the coordinate. So this coordinate we can use in order to determine the moment of the system, and also the frontal area of the particle. It is revealed from the expression that the frontal area of the particle is no longer a circular one, which is the projected area of a sphere. Next page, please. This is the instantaneous lift force, similar to that of drag, but the coefficient is different. CL is the lift coefficient, which was considered to be 0.2 according to Debug and Smith, while in case of the drag we have considered the Morse and Alexander's formula. Next page, please. Now we will determine the criteria of sediment entrainment. First of all, we consider the rolling mode. In case of the rolling mode, you can see the moments are balanced. The overturning moment is equal to or less than the stabilizing moment. Then only the particle can roll. The sign of equality provides us the criterion for the entrainment, threshold of entrainment, while the inequality sign, that is the greater than sign, implies the entrainment. When we consider the moment, when we take the moment about the pivoting point and considering the force system, we get equation 11. Next page, please. Equation 12. Already I told you about the threshold criterion and the criterion for grain entrainment in rolling mode. And finally, once the expressions for forces are inserted in the expression of rolling mode, then we get this equation. In this equation, it is shown in the form of quadratic of the velocity at the particle level. The capital Xi sign signifies the rolling threshold, while E refers to the entrainment condition in rolling mode, criterion in rolling mode. Next page, please. Thank you. This is the sliding mode. Equation is very simple. Only the friction equation is considered. The drag is balanced. Hydrodynamic is balanced. Drag is balanced by the resistance. So that is why Coulomb's frictional resistance is to be included here. And when we, next page please, when we substitute the expression for the forces, we get the condition for the threshold in sliding mode and also the condition for entrainment of grain entrainment in sliding mode. Next page, please. This is the lifting mode. Equation is very simple. FL equaling FG. That means the instantaneous lift is either equal or greater than a subpart rotating particle. From the equation expression of the forces, we get next page, we get the criterion for the threshold motion and also the grain entrainment. Now we have all three cases. Now if we compare, next page please. If we compare all three cases, then it is found to be that the lifting threshold value is the highest value, and rolling threshold value is the lowest value and the sliding threshold value is the intermediate value. So these are the three things we can be concluded from these equations if we study the equations closely. Now here so far I have talked about the time averaged velocity, not about the velocity fluctuations due to the turbulence, which is to be included here. The velocity fluctuations here, the horizontal turbulence intensity, which takes into account the velocity fluctuations in the horizontal direction, is to be included because of the fact several experimentations have proven that the horizontal turbulence intensity has had a role to motivate the particle to dislodge from its own position and also to motivate the particle to transport. Now, once the turbulence intensity is included in the formulation, then we can come up with three cases: rolling, sliding, and lifting threshold cases. And they are expressed in non-dimensional form. It is in the page number 39. Page number 39, please. Yes. So it is expressed in terms of Shields parameter. This is the way those who are working on sediment transport. So this is the traditional way to express the sediment entrainment. Next page, please. We need to determine the lever arm. Again, we have to go back to the geometry. We have to consider the vertical lever arm and the horizontal lever arm in the form of Lx. Next page, please, and Lz. Next page, please. Yes, thank you. So the horizontal lever arm is given by Lx. The calculations are shown, and the vertical lever arm is given by Lz. Everything is expressed in non-dimensional form. Next page, please. So here the flow regimes are shown, and accordingly we have to consider the velocity profile, because in our expression the velocity at the particle is squared. There are flow regimes: smooth flow, rough flow, and transition. The smooth flow occurs when the roughness, in this case, the sediment grains are submerged within the viscous sublayer. That means the information of the sediment grains are not transported to the main fluid domain. Then next case is the rough flow case. Here the viscous sublayer is not possible to form because of the fact the grains are large enough. For this reason, information of the roughness or the signature of the roughness directly goes to the main flow domain. So the flow is considered to be the rough flow, and the third case considered to be the transitional flow, where the roughness are in the order of the viscous sublayer thickness. I have to say one thing. We may loosely say that bed is rough, bed is smooth, but hydraulically it has got less meaning, because hydraulically we always say in terms of flow, not in terms of the bed roughness: smooth flow, rough flow, and transitional flow. This is the usual practice to designate the flow. Next page, please. In case of the transitional flow, the Richards equation, velocity equation, can be used. Transitional flow is ascertained from the value of the shear Reynolds number. In case of shear Reynolds number, the shear velocity or the U star is used, and as the characteristics length, the Nicorasse equivalent sand roughness is used, Ks. So when the value of R star is within 3 to 70, then the bed is considered to be a transitional flow case. Now for this flow, we can use Richards equation. There is an advantage that this equation can be extendable to the smooth flow case as well. So that's why we have taken the advantage of that. In case of rough flow, next page please. In case of hydraulically rough flow, we can readily use the universal logarithmic law. The case for the sediment transport can be considered to be a function of the bed particle. Usual practice is 2D, so that value was considered. There's a debate about the universal. Next page, please. Yes, thank you. Page number 45. Here, the von Karman constant is no longer universal because there's a debate that whether it is universal or not. But in fluvial sediment transport, when we have measured the velocity, we have found there is a deviation. In fact, the value of K declines, von Karman K declines from its universal value. And also the virtual bed level. The virtual bed level, if we consider the weakly mobile bed, which is our present problem, then the zero velocity level and the virtual bed level are elevated to some extent. Next page. Regarding the turbulence intensity, we can consider the formulation of Meju. This is the formula of Meju. So this is the way we can introduce the turbulence in our equation. Next page. Now, so far, I have talked about the deterministic case in grain scale, but actually it is no longer a deterministic case because the velocity that produces the different forces like drag, lift is no longer the steady velocity, it is a fluctuating velocity. So for this reason, we have to include the probabilistic concept in the theory so far developed. According to Wu and Lin, the possible law that follows the velocity fluctuations is the log normal distribution, and the positive horizontal velocity fluctuation near the bed is responsible for the entrainment of the sediment. This is the diagram which shows again the three different modes: rolling, sliding, and lifting, and at the same time the velocity fluctuations. And already we have worked out that the lifting threshold is the highest. It offers the highest value for the velocity, and the sliding threshold provides the intermediate value and the rolling বন্ধ করে দাও না এটা, and rolling threshold provides the least value. ঠিক আছে, ছেড়ে দাও। Now this is the probability distribution. Now we have to consider it very precisely. You can see the probability distribution in the left hand side. The rolling and lifting probabilities are considered. Rolling and lifting threshold values are also shown. In the red portion, this is the portion within the rolling and lifting, and the blue portion is the zone beyond the lifting. So if the velocity lies within the red zone, then the particle can only roll. It cannot lift because the value has not crossed the L limit. Now, if we consider the value within blue zone, then the particles can roll and also can lift. Definitely the question arises, how is it possible the particle can roll and also can lift? Its meaning is that in the next page I have written it. It signifies that the grains are lifted off the bed as they begin to roll. The same thing is happening in case of the sliding and the lifting. For the purple color portion, if the value of U belongs, then the sliding mode is only plausible. But if it crosses the value of Chi L, then again the particle can enter in both in sliding and lifting mode. That means the grains are lifted off the bed when they begin to roll. So with this concept, we'll go for the probabilistic aspects now. Next page, please. Thank you. So our probability distribution is a log normal distribution. So this is the mathematical formulation of the log normal distribution. Then next, please, in rolling mode, applying the log normal distribution, we get this expression. I do not go into the details. Using the error function, we can simplify the probability of rolling mode. Then similar way, in the next page, we can calculate the probability, sediment probability for sliding mode, and in page number 56, probability of lifting mode. So all the modes are calculated in terms of their entrainment probabilities. Now, when we insert the expressions already we have worked out, and also use some other additional notations in order to accommodate them in two lines. These are the expressions for the rolling, sliding, and in the next page, lifting. Thank you. This is the lifting, and these are the notations. So now we have everything. We have formulated the probability of 3 different modes. We have also formulated the criteria for the sediment entrainment in 3 different modes. Next page, please. So far, I talked about the grain scale. Grain scale of all the 4 systems are in grain scale. Now we have to project our knowledge into the continuum scale, because of the fact in the nature a single grain is not transported. The grains are transported as a bulk. So now we have to transmit our knowledge of the grain scale to the continuum scale. Next, yes, page number 60. In the top figure, the bed load flux in continuum scale is shown, while in terms of grain scale, in terms of a saltating motion of a single particle, this is the representative figure. That means the figure number B. Yes, next is the mathematical formulation. We have to determine the exchange time. That is important. And the number of the particles entrained. According to Hans Einstein, the lifting mode, and also according to Bagnard, the lifting mode is the pertinent mode to consider for the bed load calculation. So lifting mode, that means the lifting probability is included in order to calculate the number of grains entrained into the bed load layer. This is the criteria of sediment entrainment in bed load. The ratio of the lead force to the submerged weight is considered. Obviously, if lift is greater than the submerged weight, the sediment entrainment starts. Next page, please. This is the determination of the exchange time. Unlike Einstein, Hans Einstein, who considered the fall velocity, the ratio of the diameter of the particle to the fall velocity, here Hu and Hugh recommended that instead of fall velocity, it is desirable to consider the shear velocity. That's why this modification is done here. Next page, please. The bed load flux is calculated in the first equation, and in equation number 42, its non-dimensional form is given, which is called bed load intensity flux. So in continuum scale, we have formulated also the bed load flux. Next page, please. In order to calculate bed load flux, we need some values of the coefficient and the constants. So they were calibrated from the data of several investigators, as shown here. Next page, yes, page number 66. The calculations, first the calculation was done for the sediment threshold for the uniform sediment when we consider the diameter ratio is unity. Yes, the rolling threshold, sliding threshold and lifting threshold curves shown. Rolling, in case of rolling threshold, it is obvious that it declines with an increasing R star, reaching to a minimum value, and then it increases, finally becoming constant with R star. Some sliding threshold has had the similar kind of curve, and in case of lifting threshold, the curve is monotonically decreasing and then reaching a constant value beyond 70. When we plot Shields diagram and the experimental values, it belongs to the sliding and lifting mode. So that is why from here it can be concluded the real threshold is the case which is in between the sliding and the lifting. Next, yes. Next page, sorry, no, page number
71.
70, ma'am.
70.
Yes, no problem. Here the probability of rolling, sliding, and lifting modes are shown. Probability of rolling increases, reaches its summit and then declines. The probability of sliding has also the similar nature with a slight shift. But probability of lifting is completely different. It is monotonically increasing. And we can see when the peak of probability of rolling reaches the probability of lifting starts from that point. And that point refers to the threshold value of Shields parameter for the rough flow, because of the fact here the the larger particles are considered. So that refers to the rough flow. Next page, I have discussed already. Next page, page number 72, I have discussed. Page number 73, yes. So previously we have considered a single particle, but here if we vary the particle diameter, we get two lifting threshold curves. Please remain on page number 73, ma'am. So these two lifting threshold curves merge at some point with an increase in theta, and thereafter we get a single curve. Next page, please. These two curves refers to the values of diameters 1.8 and 0.8 millimeter. These are called the right bound curve and left bound curve. So within these two sizes, all other sizes would vary within this domain only. However, if we consider any particle value below 0.8 or above 1.8, then there is no change of the curve. This is one of the characteristics of these two curves, unique characteristic. That's why the right and left bound curves are considered to be the frozen curves. Next, you can go to slide number 77 because I have discussed everything. 77. Yes, here the bed load flux function is shown. This curve can be used to determine the bed load transport rate for a given flow intensity, which is nothing but the reciprocal of the Shields parameter. Here also we find that there are two frozen curves and they meet at a point at around phi b equal to unity, and thereafter we get a single curve. So all the diameter, all other diameters would vary within these two curves. Next page. So these two frozen curves refer to the particle diameter 0.8 and 4 millimeter, beyond which we do not get any extra curve. All the curves overlap on these two curves. Next. So the conclusions are, go to the conclusion slide. Conclusions are the entrainment threshold lies in between the sliding and the lifting mode, and entrainment and the rolling entrainment of rolling and sliding modes increase with an increasing Shields parameter, and thereafter after reaching their peak they decline. The peak entrainment probability of rolling corresponds to the threshold Shields parameter in rough flow. Next slide, please. The threshold of entrainment of lifting mode corresponds to the lifting, sediment threshold Shields parameter in rough flow, and the main contributions are the entrainment probability formulations. Next, in continuum scale, we have given the curve for the estimation of bed load flux and also the formulation. Next slide. Now, future research scope. Future research scope, slide number 84, ma'am.
Yes.
Slide number 84. Yes, thank you. After the discovery of bursting phenomena, we have investigated a lot. So what's the role of bursting towards sediment entrainment? Unfortunately, the inclusion of bursting phenomenon in the modeling is not there. So maybe for the upcoming generation, this is my proposal that they can try to include the bursting phenomenon in the revised sediment entrainment and sediment threshold model. Next slide, please. Here, I can say a few more words how to include them. If we look at the bursting phenomenon in the rough bed, we get in the first figure, we can see the small scale eddies in presence of the large scale motions. And if we consider the high speed and the low speed fluid zones, we have a figure that is given in figure B, and also the Kolk kind of vortices which is ejected from the bed. So these are the schematic view of the experimental results, and also this is followed by the sediment bursting event in terms of the faster moving flow zone, followed by the slower moving flow zone, and so on. So in the faster moving flow zone, sediment particles can be picked up, and these flow zones also shift with the time. And in the slower moving fluid zone, the sediment particles can be deposited over a period of time. Next slide. These are the references. Thank you very much. Thank you.
Thank you so much, sir, for a wonderful talk. I would like to invite some of the questions from the participants, please. Please unmute yourself and ask the question. Yes, sir. Raju, sir, please.
My name is K.G. Rangaraju. I worked at the University of Roorkee or IIT Roorkee later. I was a student of Professor R.J. Garde, who I believe was the person who put India on the sediment map of the world. He did pioneering work in the 1960s. Sediment transport. We are extremely happy to note that Professor Day is the current chair of this, and he's doing an excellent job, and my hearty congratulations to him on this issue. I would just like to pose a small question to Professor Day. In all the diagrams you have for the entrainment and bed load, which are dimensionless, why do you have different curves for different sediment sizes? The 0.4 millimeter, 1.8, I thought it should be dimensionless.
Even then, if it is made dimensionless, actually these are made dimensionless, and from there I have decoded the values of the sediment diameters. Okay, so actually when the calculations are done, we have considered certain diameters, and thereafter if we decode them, then we can get the dimensional values from the dimensionless curves. It has got the dimensionless value, Professor. If you want to know, I can share the dimension. Professor Rangaraju, I can share the dimensionless values also. This is published in Journal of Engineering Mechanics, ASC. So I can also open and I can share the dimensionless value.
That's fine.
Okay.
Okay, that's fine. That's fine. Thank you.
It has got corresponding dimensionless value.
Okay, thank you.
I invite further questions, if any. Please unmute yourself and speak. No raised hands, sir. So I think the presentation was self-explanatory. Now I request our Pro Vice Chancellor, sir, Professor P.K. Nanda, sir, to give vote of thanks.
Thank you, madam. Good evening, everybody. I think it is a wonderful talk and for the lucid presentation. Professor Dey has, I think, addressed a very emergent problem and very intricate issues. I think for people, those who are working in this area will definitely have a kind of a key takeaways from his talk. So on behalf of our INE Bhubaneswar chapter and SO University and IMMT, I extend heartfelt thanks to Professor Dey, who has spared his valuable time and he's shared his expertise among all the distinguished listeners, distinguished participants. In this area, I think people will be greatly benefited. And I thank him for, I think, sharing his domain knowledge with all of us and for the lucid presentation. And I hope, I think many young people who are working in this area will definitely take it forward. I thank Professor Damodara Acharya to, I think, spearhead this program by inviting eminent scientists and the speakers, professors in different areas. And I thank Dr. Renu Sharma and his team for coordinating the whole event. I thank our Honorable Vice Chancellor and Professor Ashok Mahapatra and Professor IMT Director, Professor Basu, for sharing their inputs regarding the institutional, I think, details. I thank all the distinguished participants. I thank Professor Mishra to introduce the speaker, today's speaker, nicely with a problem and his childhood experience. I thank all the distinguished listeners and distinguished persons, faculty colleagues, students who participated actively in today's talk. Thank you, everybody. Thank you all. Good night.
Thank you, Professor Dey, profusely for your excellent talk. And this is particularly interesting that your supervisor, Professor Rangaraju, he was present here. It is indeed a great pleasure for any teacher to see that after so many years that his student is actually giving some talk of this type. And here I may just mention that I learned a little bit of, say, fluid mechanics, not actually this fluid dynamics, etc., from one of my professor, Professor N. Vittal, who later on joined IIT Roorkee or Roorkee University. Professor Rangaraju may be knowing him. Am I correct, sir? Oh, I think it is not here. Thank you very much.
Thank you, Professor Acharya. Actually, Professor Rangaraju is my guru.
He is your guru. That's what I'm telling you. It is always pleasure to keep some talk before the guru.
My supervisor was Professor G.L.N. Shastri.
G.L.N. Shastri. Okay.
You know him.
Mm-hmm.
Thank you.
Thank you. Thank you, Professor Dey.
Okay, bye.
And one more thing, do you have with your permission to share the slides with others?
Sure.
Okay.
It's my
And
pleasure.
we will give a small memento and to all our speakers, and that memento will be posted to you, and we'll share your lectures slides with all others.
Thank you, Professor.
Hey, thank you so much. I'm so happy.
Namaste, sir. Thank you so much for
Thank
joining.
you, sir.
Namaste.